Welcome to Western Sports Science. Today we'll be analyzing how to perform a back squat. The squat is the most complex, advanced movement performed in weightlifting. Squat form consists of the feet a little wider than shoulder width, with the bar placed over the trapezius or upper back. The hands will be gripping the bar in a supinated position, with the hips thrusted slightly forward and the abdominals flexed. This will force the back to have a small arch in the lower region. On the descent, the chest is held high while the hips and gluteus maximus move downward to create a 90-degree angle. The knees and the thighs are parallel to the floor. Power is created as you push against the floor and the weight moves up to the start position. The overall movement of the squat is located in the transverse plane. The knee angle of Hunter squat is at 50 degrees. His ankle angle is at 74 degrees, and his hips are at 55 degrees. The main muscles used while performing a squat are the rectus abdominis, located within the abdominals, the erector spinae in the lower back, the gluteus maximus and medius in the buttocks, the rectus femoris, vastus lateralis, as well as the medialis in the quads, the sartorius, biceps femoris, and the semitendinosus, which are also referred to as the hamstrings, and then the gastrocnemius and soleus, which are also referred to as the calves. Now Trace is going to provide a mathematical explanation of the amount of work and power required for Hunter squats.
So before we start calculating, we're just going to tell you some basic information that you probably wouldn't know if I didn't tell you. So our subject's weight, 195 pounds. So in order to get all the right calculations, we had to convert that into kilograms, which ended up being 88.45. In order to find the work done in a squat, we have to find the force first. So here's the equation used to find force. And the G's, which is gravity, will remain a constant, as well as the little m. And eventually we will end up with the power. So for the 135-pound squat, we calculated that to be 61.24 kilograms. So we got F equals 88.45 kilograms times gravity plus the weight of the squat, which is 61.24 kilograms, also times gravity, and we get F equals 1,468.4 newtons of force. So what do we do with that? Well, we turn that into work by going work equals 1,468.4 newtons. So in order to find the work, we need the distance traveled by Hunter during each squat, which was 68 centimeters, which we converted into meters at 0.68 meters. So we times the force by the amount of distance traveled, and you get work equals 998.24 joules. Now, last but not least, in order to get the power, fairly simple. Power equals the watts, or the work, so 998.24 joules over 1.78 seconds, which is how long it took him to complete the squat, equals 560 watts. That's the amount of power done in his first squat, and the cool thing is that's about enough power to power about 9 light bulbs in your average house, 9 60-watt light bulbs. Now, the only thing that's going to change for the 225-pound squat is the kilograms that it converts to. So we're using the same stuff that we used for the first calculations, but the only thing that's different is the squat. So we got the force here, Hunter's weight times gravity, plus the weight of the bar, as well as times gravity. So the force that we get for this one is 1,868.56 newtons. So, like before, you take the newtons, you plug them into this equation to get the work. So you multiply the amount of newtons by the distance traveled in the squat, and that gets us to 1270.64 joules. Now, as you can see, that's more work done in this one than the previous one because more weight. And since this hunter took the same amount of time in each of these squats, we divided the amount of joules by the amount of seconds in order to get the power. Now, for this one, since the work was more, that equates to the power being more, and the power for this one is 713.84 watts. Back at it again with the calculations. For 315 pounds, we got that into 142.88 kilograms. Now, the only thing that's going to be different with this one is that the time that it took Hunter to perform the squat is 0.03 seconds faster than the previous ones. So that might shift the data a little bit, but everything else is remaining consistent. So the force for the 315 pound squat on his back, we calculated out to 2,269.3 newtons. So in order to get the work, the same amount of distance was traveled as the other previous squats. So we multiplied that by 0.68 by 2,269.3 to get our total work in joules, which is right here, 1,543.12 joules. And as you can see here, the time is different. So we did the joules divided by the time to get 881.78 watts performed with a 315 pound squat. So for the last squat that we performed during this, Hunter squatted 405 pounds, the most weight we did, and that came out to 183.71 kilograms. So we calculated out all the stuff after we did this. The force of the last squat was 2,669.89 newtons. Just like every other thing we've done before, you just put this into that equation in order to get the work times the displacement or the amount of distance traveled, and the work equals 1,815.53 joules right here. And the thing that's funny about this one was this squat, since it was way heavier, took Hunter a lot more time just because, you know, it's a lot more weight. So our time in this one is a lot different than the other ones. So we got the power equals the work done, which is 1815.53 divided by 2.6 this time, which is why we end up with a little bit lower amount of watts right here, because the this value is different. So as you can see over here, for each squat that we did, the first 3 times were fairly consistent, then the last one was not as consistent, but generally other than the last one, the more weight, the more watts are produced.
Now that we have analyzed the amount of work and power in Hunter's squat, we will observe the amount needed in world record holder Donnie Thompson's squat. He is not related to our Thompson, however.
All right, so here we have all the equations used and needed to find the amount of watts, aka the power, used in Donnie Thompson's squat world record of 1,260 pounds, which calculates into 571.5 kilograms. And another quick, just a little bit of information, he weighs approximately 370 pounds, and that is 167.83 kgs. So, like all the other boring stuff we did earlier, I got the force with all these numbers here, came out with a force of 7,252.8 newtons, which is a larger force than we saw with any of Hunter's squats. The work performed in his squat also was way more joules than any of Hunter's because he had a ridiculous amount of weight on his back. But it took him about 6.43 seconds to complete the squat, which is why the watts, you probably expect a little bit more, but Yeah, since it took him so long. But we got 789.57 watts done in his squat over a 6.43 second time.
Thank you for watching our sports science. We are sports
And science!